Welcome to the mini lecture for Module 2 on organizing, displaying, and describing data. For this mini lecture, I'm going to be covering a few of the principles related to graphs and especially frequency distributions and bar graphs. So the overall objectives for this module that expand, of course, beyond what this mini lecture is that you should be able to identify data distributions by their shape, recognize skewed and symmetric histograms, differentiate between frequency polygons, histograms, bar graphs, and line graphs, and identify problematic issues with graphs that impact interpretability. So why is graphing important? It is used as a valuable way to summarize data and see patterns. So once you've gone out and collected a bunch of data, you want to get some insight. So you can plot your data and see if the data is clumped around some particular value. If you're looking at the distribution of your data across the range of values that are possible, you could see if the data tend to cluster around large values or small values, or to see if the data are spread out equally and have a uniform distribution. These 3 points here all refer to frequency histograms and the patterns that you can see. In addition, if you had data assigned to different groups and you'd make a bar graph, you could say, are the data mostly represented in one certain group or another one? An important tip when you're looking at patterns in your data is that when you then later go on and do statistical analysis, that you should not be surprised by the results of your statistical analysis because you've graphed it, and so you should already have gained some insight. If after doing the analysis, the conclusions are completely opposite, then something might be erroneous along the way. So frequency distributions are defined as the number of observations for some particular value. So in this case, when you have numeric data, you divide the range, so the maximum value minus the minimum value, into intervals, and then count the number of observations that fall into each of the intervals that have been identified by values. And so these can be simple, where each value is represented separately, or you can create small groups of data. So in this case, where you have your raw data is condensed into groups that are often equally sized. And we're going to talk about some examples here in a second. So here is some data, and it is based on looking at abnormal cardiac function in diabetic patients, and specifically at resting LVEF, which is left ventricle ejection fraction, based on 30 insulin-dependent diabetics. So this LVEF was measured for the 30 diabetic patients, and here is the data. I'm going to suggest now that you pause the video and look at just making a simple frequency distribution as a histogram. So if you pause the data, you can make that frequency histogram. Once you've completed this, move on to the next slide. So here's what the frequency distribution would look like. So we have our values of LVEF percentages across the bottom, and each of them fall into the range between 40, which was our minimum value, and 94, which was our maximum value. And even though the numbers here represent every second number, the values in between would also be counted. And then on the y-axis, we have the frequency. And when we look at this, we can see that the data definitely aren't uniform. So the values aren't falling equally across that entire range. We can look at the skew in the data, and I'm just going to superimpose a line here. And what we can see is that the data tends to be clustered around sort of the mid-70s primarily, and we would refer to this as having a negative skew because there's missing data sort of on that left side, or it'd be called left skewed. And the mode of this data, so the value that has the highest representation, would be 76. We'll talk more about things like mode and the mean in the next module. So this is the simple histogram. So now, I would say what we're going to plot next is the group frequency distribution. So here's the same data in table 2.7 that you had before, but now in table 2.8, I'm going to suggest that you pause this after I finish explaining what you should do here. So now these are grouped intervals. And in table 2.8, the ranges include units that are have intervals of 5. So write in the number of patients for each of those. And when you finish that, complete table 2.9 that now has an interval length of 10. And the point of this exercise is to then compare, what is the importance of these different interval lengths if you're actually binning numbers together versus just leaving it as individual values, where each individual value is represented. So pause the video, figure out the number of patients, and draw the frequency histograms for these before proceeding on to the next slide. Okay, there are the number of patients that you should have, so make sure that that's correct. And once you have that correct and you've made it into graphs, we can look what it looks like visually on the next slide. So here's our original frequency histogram that we had, where the unit on the across the x-axis is just values of 1, so it increases by an increment of 1 every time. And then here we have histograms at the top that has an interval length of 5. And you can see that the data could potentially here have 2 peaks, so it would look bimodal. So one peak in the sort of 60 to 70 range, and then another one in the 75 to 80 range. It also looks less skewed than the original one that we plotted as well. Perhaps still a little bit less skewed, but much less than the first one. And then when we have a histogram with an interval length of 10 at the bottom, it actually looks quite symmetrical. So this is the where the importance of the interval widths come in. So the question is, are some of the low LVEF values, are they there because they're actually real and representative, or is it because we have lower sample sizes? So it's important to consider these things when choosing the interval length. Here's just another example. This is looking at body mass of some salmon, and there's going to be 3 panels here. So the first one has the smallest increment, and then it's our frequency distribution. So this one looks bimodal with 2 peaks. If we increase the length of the interval, we still see that it appears to be bimodal with peaks. One is just under 3 kilograms, and the other one is probably around 1.5 or 1.75 kilograms. And then when we increase that interval again, the data now looks like it's very positive or right skewed and no longer looks bimodal. The other two also look like they have some positive skew going on as well. So again, it's important to consider in this case whether these 2 peaks that we see, if they're actually real, meaning are they representative of the data, or is that smaller peak just an artifact of too few observations? Because in these cases, it's not like there is a right or a wrong answer, but it is important to consider what is most representative and then how to present that information. When we have frequency distributions that have been collected from different places, we can plot that data or raw data and the frequencies therein to look at some trends. So here's data on hemoglobin concentration in men living at different altitudes, typically high altitudes, and then the relative frequencies. So the bottom 3 are at high altitudes, and then it's just a comparison to at sea level for some men. And just by looking at these histograms, you can see that the peaks for the USA, Tibet, and Ethiopia are all around 15, and that they appear to be unimodal. And then when you look at the Andes, the bulk of the data tends to be at a much higher level. So the mean value would probably be somewhere around 18 and 19, and the whole range has been shifted up from those other levels. So, like I was saying before, that if you then wanted to go and do some statistical analysis on this, you might expect that USA, Tibet, and Ethiopia would cluster together and maybe not be different from one another, but perhaps be different from the site in the Andes. So keep those things in mind as we continue to move forward. When we're graphing categorical data, remember categorical data in this case is actually going to be nominal data. So we have a frequency table showing the 10 most common causes of death in Americans between 15 and 19 years of age in 1999. We have a series of different causes and then the frequency of each of those. And there's no particular order that we would put these causes of death in, right? So that's why I said they're going to be nominal and not ordinal data, right? Remember in ordinal data from Module 1 that the order matters. Here it does not matter. And we can't create really a frequency distribution from this because frequency distributions have a continuous variable, numeric variable on their x-axis. So what we would create in this case is a bar graph. So along the x-axis here are the different types of accidents, and on the y-axis is the number of cases. But one important thing to notice is along the x-axis, these could be in a different order. There's no particular reason to put them in this order. They tend to be ranked from, the highest frequency to the lowest, and then all other causes. But other than a visual way of looking at this, there are other ways to plot this as well. They would all be as equally as correct. So keep that in mind. Because this data is nominal and the order here doesn't matter, we cannot look at anything like skew in this case, because skew is only relevant when we have a numeric variable on our x-axis. Your textbook talks about line graphs, and this is where the x-axis is ordered in some way. For example, time or something that's in some order. And then the data points on the x-axis could potentially be connected to one another to be able to make those patterns clear. Another type of plot that I'm going to mention now and we'll come back later on is a scatter plot. And a scatter plot is where we have bivariate x and y data. And what that means is for any individual data point that we have, there's a classification and a value of the x-axis data point and the y-axis data point for one particular observation. So a couple examples that I'll show you quickly here. On the x-axis here is the number of community hospitals, and then on the y-axis is the number of deaths. So when you look at a point, for example, that's at 50 community hospitals, the number of deaths there might be around 7,000, for instance. So each of those data points is unique. Another example here is the years of smoking and lung function, where for a given number of years of smoking, so say 55, there would be one or more data points associated with that, with people who've smoked for 55 years. What is their lung function? And here we're seeing a negative relationship. So that concludes this mini lecture.